In this video, we will introduce something called logarithmic differentiation, which allows us to take functions, maybe of the form given here, that we could previously differentiate, but the work is a bit messy, and now we're going to make it a bit less work. So how we're going to go about that is we're going to look at this function and say it's a product, and each of those products are raised to powers. So the natural log would be something that nicely breaks this up into pieces. And to see what I mean here, let's just go ahead and take the natural log of both sides. So we would have on the left-hand side the natural log of y. Now on the right-hand side, if you imagine taking the natural log of that, and I'm going to just go ahead and write it all out. X squared plus 2 squared times x squared plus 4 to the fourth. The properties of the natural log tell us that we can break it up into the natural log of the first thing, x squared plus 2 squared. But instead of putting the square inside, I'm going to pull it outside as a constant, plus the natural log of that second function, x squared plus 4 to the fourth. But once again, properties of natural logs, instead of having it raised to a fourth power inside the ln, I'm going to pull that out front. So using properties of natural logs, we've taken this expression we had on the right-hand side, and we've written it in a much more convenient format, at least from the perspective of differentiation. So what I'm going to do now is differentiate both sides with respect to x. And note when we differentiate with respect to x on the left-hand side, that really is an implicit derivative, whereas on the right-hand side, it's just a standard old or explicit derivative. So the derivative of natural log of y with respect to x. The rule of thumb, because it's implicit, note the y and the x variable do not agree. You differentiate the natural log of y exactly as you would like to. That is, its derivative is 1 over y. And then you multiply by y prime. And then on the right-hand side, just go through and differentiate each term. So 2 times, well, natural log of x squared plus 2, chain rule problem. 1 over, we evaluate at the inside function. We multiply by the derivative of the inside function. Plus 4 times a very similar thing here. Natural log of x squared plus 4, chain rule. We take the derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. What we would like to figure out is dy dx, or call it y prime. So y prime is going to equal to, well, what we need to do is take this y, which is in the bottom on the left, and multiply it by both sides. So what I'm going to do here is essentially multiply by y. But instead of writing y, I'm going to go back up to the top and put it in terms of how it was originally defined. So that would be x squared plus 2 squared times x squared plus 4 to the fourth. So y, and then I'm going to go ahead and multiply it by everything that we already had on the right. So that would be 4x over x squared plus 2 plus 8x over x squared plus 4. Now, as mentioned, you could most certainly have used kind of previous rules of differentiation, so a product rule combined with two chain rules. But logarithmic differentiation gives us a different approach. And just to summarize the steps used here, when you're going to differentiate logarithmically, which works really well when you have functions which have lots of powers, products, and quotients, you take the natural log of both sides of the equation and you use those properties of the natural log to simplify. Once you've done so, you implicitly differentiate both sides with respect to x, and then you very quickly isolate the dy dx. Essentially, you multiply both sides by y. So another common example. So once again, you could certainly go ahead and differentiate this. You could use the quotient rule to get started. Both of the remaining derivatives would involve the chain rule. We're going to go ahead and use logarithmic differentiation. And the reason logarithmic differentiation applies well, you have quotients and powers. So take the natural log of both sides. Natural log of y equals, and we're just going to jump right into it on the right. So you have the natural log of something divided by something, which means you get the natural log of the top. So that would be the natural log of the square root of 1 minus x squared. But remember, square root is really raising to a 1/2 power, and instead of putting that 1/2 power inside the log, you can pull it out as a constant. Similarly, we now subtract away the natural log of what's in the denominator. So x plus 1 to the 2/3, 2/3 at power inside the natural log becomes a constant outside. So in this more simplified form, the derivative is easier for us. So what we are going to do is differentiate implicitly with respect to x. On the left-hand side, just as it was in the previous slide, we'll have 1 over y times y prime. And note the derivative of the natural log y with respect to x, something we call the logarithmic derivative, is always going to be y prime over y. Now on the right, just going through and doing the chain rule twice, we have 1/2 times 1 over 1 minus x squared multiplied by minus 2x. Then minus 2/3 times 1 over x plus 1. And the chain rule here, multiply by the derivative of the inside function, you really just multiply by 1. So note in this first fraction, the 2 and the 2 go away. So y prime is now equal to y, and we're just going to cut and paste that y from above, square root 1 minus x squared, all divided by x plus 1 to the 2/3 power. So that's just multiplying both sides by y. And then we're just going to cut and paste what we have on the right-hand side above. So that would be minus x over 1 minus x squared minus 2/3 1 over x plus 1. And this entire quantity that we have represents dy dx, or let's say y prime.